how you can get better quality and productivity using two of the JasperGold Designer applications, Superlint and CDC. I'm Kanwar Pal Singh and I work as a product engineering architect in Cadence's JasperGold product division. I have around 20 years of EDA experience, and my experience has been primarily in the verification technologies, which includes simulation and formal verification. For the last about 10 years, I have been mainly focused on the RTL sign-off checks domain, which includes LINT, DFT, CDC, and RDC, and focused on how to make this RTL sign-off more efficient and faster, which is also the topic of our session today.
Hello everyone, my name is Bijitendra Mitra and I'm working as a product engineering architect for the Jasper Gold family of products. And my focus is primarily on developing and deploying the CDC app along with RTL sign-off solutions. And I have over 20 years of experience, and out of which the past 15 years I have been working on formal verification of IPs and SOCs, along with tool development and verification methodology development. So today I'll be the co-speaker for Kanwar, and I'll walk you through the CDC section of this tutorial.
All right, so this is our agenda for today. So we'll start by discussing the big picture. We'll have the look at the big picture. Then we'll move to talking about augmented sign-off, which will be covered in two parts. One is the autoformal checks using JasperGold Superlint, which will be followed by a demo. And then we'll talk about functional and metastability aware verification using JasperGold CDC, and that will also be followed by a demo. Then we'll conclude and we'll have around 10 minutes in the end for questions. Okay, so let's start with the big picture here. So we all know that, if we can catch our bugs early in the design cycle, that is always beneficial from the point of view of cost and also the design schedule. So the effort, to fix the bugs, if you find those downstream, is much higher. So if you look at this, simple effort to fix bug versus time graph, then, if you can catch it early, it is much better. But as the bug travels along, it becomes much more costly to catch the bugs and will definitely increase your cost. So, there's a very common term which we use here, shift left. So if you can shift left your checking and you can catch bugs early in the design cycle, that is very beneficial. I think that's very we have talked, this has been talked about in various forums and papers and all. Okay, so if we look at the big picture now, so typical RTL sign-off includes, the checking of your RTL against a set of comprehensive structural LINT, DFT, RDC checks. This is typically what has been the practice at the RTL stage. All the checks are mostly automatic, and the user, which is the designer here, really provides the RTL mostly. And in case of DFT and CDC, that is also accompanied with constraints. So that's what typically we've been doing in this space. So let's call this as automatic structural checks. But from our experience, working with different users and also from our experience working in this domain, what we have seen is that if you just do the structural sign-off, then there is a good possibility of still having bugs in your design. And to cover that, for a comprehensive sign-off, you need to really augment your structural checking with automatic functional checks. So that is what we have seen and experienced. And that's also, the feedback which we have got from various customers. So what this means is that you need to augment your checks with high value code reachability and functional checks, and also the functional CDC and RDC to augment the CDC RDC checking. So let's call this as automatic functional checks. So Jasper Gold is, uniquely positioned to give true integrated solution for both uh, structural checks and the automatic functional checks. And these automatic functional checks are, you know, uh, manifested as autoformal checks in the JasperGold Superlint application. We'll talk about that. And functional RDC and CDC checks in the CDC application, and also the metastability aware verification. So if you bring all this together, that is where you will see that you can get better quality and faster sign off. This may look like more work, but actually at the end of the day, this leads to faster sign off of your RTL, because it really augments the checking and makes it much more efficient and productive. So let's look at each of these pieces separately. So why auto formal? So both the words are important here, auto and formal. So we are talking about RTL sign off, which is typically something which is done by the designers. So automation is the key here. We cannot have introduce another step in the RTL sign off, which requires a lot of work, and people need to write their own checkers and constraints. So whatever solution which needs to be brought here, it has to be automatic, such that it can easily augment the structural checking. And why formal? Formal is exhaustive. I think you all must be knowing this. And no test bench is needed, and you can really start early. So if you look at the design scenarios and your time graph, in case of simulation, there is a ramp up curve and there is a setup time needed, and the time which you will find your corner case bug maybe later in the time, once you have a good setup for simulation. Vis-a-vis on the formal side, the curve is quite different, because you can really start early and you can reach your first corner case bug much earlier than what you will achieve in simulation. So when you bring in this automatic checks and leverage formal engines to do that, this is what the auto formal checks provide, and can really augment your structural checking and make it much more comprehensive. So this is the shift left I mentioned when I talked about trying to catch bugs early in the design cycle. So let's look at an example here. A finite state machine example of a deadlock situation. So if you see here, if once you enter this state checksum and this signal, if this never goes high, then you are deadlocked in the checksum state. There's no way out of this, right? Now, this kind of checks you cannot really catch structurally, and these are, this deadlock is a high value check to be, or high values, issue to be caught early in the RTL stage, and this can be only automatically checked with the auto formal checks. So this is an example of what I started with, that you have typical structural checks, the LINT checks, but to get more comprehensive sign off in the LINT space, you'll need to augment that with the auto formal checks, which are automatic, powered by the formal engines, and this is an example of those. So now moving over to the CDC side of it. So we talked about the LINT, sign off side of it. Now let's talk about the CDC sign off side of it. CDC sign off is still, primarily focused on structural analysis, and it actually, there's a lot of manual review in this case, because you have to really go through the violations, the waivers, you waive violations, then you sign off by manually reviewing waivers. So this is definitely error prone and takes a lot of time, right? And also CDC checking and verification is currently seen as two independent efforts. Okay, so what are you really missing if you do not do the functional CDC checks and metastability aware verification? So first is correctness of constraints, because your CDC sign off is really dependent on the quality of constraints which you provided. So, and there's a lot of reuse there, right? So you really need to make sure that are my constraints correct? The second thing is validity of waivers. You made some assumptions while you were waiving some violations, right? And the in the structural case, the waiver review is basically based on the comments. But you really need to make sure that the underlying assumptions of my waivers are valid. So you have to really check that. And then you need to guarantee that your design is immune to metastability effects. So you need to make sure that under the metastability situations, my design behaves correctly. So only once you bring these three aspects into your CDC, that's when you can say that my CDC, sign off is fully comprehensive, and I can actually, link in the functional verification here and make the whole sign off much more, efficient. And again, this may look like more work, but it at the end of the day, by automating these things, this brings in a lot of confidence in your CDC sign off, and helps you to shift left and can eventually accelerate your sign off. So that's how the auto augmenting lint checks with the autoformal, and augmenting your structural CDC checks with and constraint sign off, valid waiver sign off, and metastability aware verification can really help you get much more comprehensive sign off. Okay, so let's talk about the autoformal piece a little more, and what capabilities we have in the JasperGold Superlint app to support what I just said in terms of getting a comprehensive sign off with autoformal, augmenting your lint. And we'll have a short demo to go through this. So there are a lot of autoformal checks in the available as something where the properties can be automatically extracted from the RTL, and then formal engines can be used to formally prove and make sure that the design functionality is correct. There is dead code, X assignment reachability. For finite state machines, we have reachability and live log deadlock checks, checks on signals, case statements, out of bound indexing, arithmetic overflow, and bus contention. So this is the list of all the checks which are available in the JasperGold Superlint app in terms of the autoformal checks. And in terms of flow, so as I initially said, it has to be automatic. So it shouldn't be like, another step, another effort on the designer side. So in terms of flow for the lint, it is pretty simple. You have a rule configuration. You feed it into the lint extraction, and do your lint checking. Then there is this analysis step, the debug step, where you create your waivers. You look at your violations to see how you're progressing, and then there is a sign off report which you generate. Now the augmented checking here, which is the autoformal, nicely fits into the flow because it's the same infrastructure in terms of rule configuration comes from the same rule file. You might need some kind of design configuration, not too much in terms of clocks, reset, some signal configuration. And from there on, the checking and the analysis, debug, everything is the same environment as you have for the lint checks. And when it comes to analysis of this in the GUI, uh, everything is shown in the same violation tree, and the whole experience from there on is the same as your structural lint checks. So that's how everything is integrated nicely integrated into one seamless flow here. Um, to help with the designer productivity, there are a lot of productivity features in the Superlint application. And there is a customized failure analysis, a persistent waivers, grouping to help with the navigation of the violations. There's a observability enabled debug, and there's a very unique feature which the JasperGold Superlint application provides, because you're running lint and you're running autoformal, so you can really leverage the autoformal to reduce and refine the lint results. And when I say reduce, I mean reduce noise and refine the lint results. So there's a lot of capabilities here. And then you have all kind of debug capabilities: source browser, FSM graph, schematic, waveform to debug the violations. So let's look at this in a quick demo. Let me uh, stop sharing here and share the demo screen so that you can see the demo here. So I hope you can see my Unix machine. So, I talked about the flow, the rule configuration, and also how easy it is to run the autoformal along with the structural lint. So what I have on the right actually first is the rule file. So everything is organized in one rule file. We have the domains, length, DFT, autoformal. You can see here. Each of these has the categories. So it's all in the one rule file. You don't need any separate configuration for autoformal. And each of these categories further has the checks inside those. So this is all in one rule file. And in terms of running, you can create your own custom rule file. So this is your command to just load the rule file. Then you analyze and elaborate the design. There's a configuration of clocks and reset only required for autoformal. Then you really do your checks, and for the autoformal you prove, and you generate the reports and save the database if you want to restore it for analysis again. So if I run this script just to make it quicker and save on time, I have run this already, and I have a GUI open with the results. Okay. So, first of all, when you run, you get the design build. So during the design build, what kind of, violations you get. So you get those. And then in terms of rule violations, you will see all this, as I mentioned, in one tree. For all the different domains, you have lint, you have DFT, and then you have autoformal. So all the violations are in the same tree. You can see these here. Okay. Now, in terms of the debug, the coding styles and all, you can always look at the violation. For example, I'm looking at the overflow violations. You can click on a violation. You can look at the source code on the right side, and you can, if you want to edit the source code, you can say, okay, edit source, and that will open the editor where you can fix the violation. Or if you decide to waive, you can right click and say I want to waive. Okay, so that's the typical how you maneuver the structural lint violations. For this, for the more structural and design which need to be looked from a schematic perspective, there is a schematic capability. You can click on this and you can say show schematic. So this will open the schematic which will show you the violation, and the nets which contribute to the violation are highlighted in red. So you can really debug your schematic by zooming in, zooming out, by trace the fan in. You can do all that in the schematic. Okay. The On the autoformal side, you can really look at a violation. You can say, okay, I want to, look at the waveform of this. So you can say, open the visualize trace. So this will open the waveform using the JasperGold Visualize debugger, which is one of the best RTL debuggers available in the market. So here you can, click on something. You can say, okay, why did this get why, and how did it get this value? So you can do all that analysis here. Okay, and one last thing quickly to cover here is that I talked about leveraging autoformal for lint. So for that, I can change my customized layout to formal property layout. So I have access to the formal uh, tools, and then I can say, okay, leverage the results. So what it does is that if there is a violation which was reported by lint, but the formal engine said there is no such violation, it will waive that. So you will see the waiver here. Okay. So this is, a quick view into the how the things work in the Superlint application. So I will just summarize it here, and then have move it over to Bijit to cover the rest of the CDC side of things. So in terms of Superlint, we have the structural lint DFT checks, we have the autoformal checks, and all this is complemented with the best-in-class debug using the JasperGold Visualize environment. And this really helps you get a comprehensive, sign off of the RTL, where you not only do the structural lint checks, but augment those with your best-in-class formal engine enabled for autoformal checks. Over to you, Bijit.
Thanks, Kanwar. Let me, could you please, can you see my slides?
Yes.
Okay, great. As Kanwar said, that we are talking about augmenting your sign-off with features which would give you better quality and a faster sign-off. So towards that, now we are going to look at how you can augment your CDC RDC sign-off with functional checks and metastability aware verification using JasperGold CDC app, and we'll follow with a demo. So first, a quick recap of why functional CDC RDC analysis and metastability aware verification is important. As Kanwar mentioned, that in the traditional or conventional CDC RDC flow, there are a few gaps that exists. First is, of course, correctness of analysis constraints. So today the user would provide a set of constraints which are used for the CDC RDC analysis, but we don't really validate whether those constraints are correct. They're considered as golden. So the question remains that are my constraints correct? The second thing is validity of waivers. So typically when we waive a violation, we have an assumption towards some design functionality. We say that, okay, this is how my design is going to behave. So this is not a valid problem. So I'm going to waive this violation. But rarely we would validate that assumption about the design functionality. So the question remains that the assumptions I'm making for waiving my structural violations, are those assumptions correct? And the last thing is about metastability aware verification. So the sole purpose of doing CDC RDC analysis is to ensure that my design is tolerant to metastability effects. Now, to do that, my verification environment also needs to be metastability aware. So all these things, as you can see, validation of constraints, waivers, and even doing a metastability aware verification actually needs a linkage between the CDC RDC sign-off flow and the functional verification sign-off flow. So that is what is the key to true CDC RDC sign-off. Now let's take an example of each one of these and understand that why it is important to add these checks to your sign-off process to have a robust sign-off. So this is an example where we have an asynchronous FIFO, and the output of the FIFO goes to a status register in the APB interface. So in the first generation of the device, the user didn't bother to synchronize this path, although it is a CDC crossing between CLK and PCLK domains. He didn't bother to synchronize it because it is going to a status register. Instead, he also declared it as a static signal because the tool won't report a violation here. Now, in the next generation of the device, this FIFO full signal is now used for generating a valid signal. So this is also part of some functional logic now, but unfortunately, this static declaration was not removed. As a result, it masked this valid glitch violation on this flop because of presence of combo logic on this CDC path. Now, had we had a way to validate the constraints, we could have caught it much earlier in the design cycle, which indicates that there is a missing verification linkage when it comes to validation of constraints. Now, let's look at validity of waivers. This is a classic example of an RDC violation where there are a couple of flops which are connected back to back with the same clock connected to them, but there are different asynchronous resets driving. So if reset 1 is asserted while reset 2 is still deasserted, the output of the first flop can make a transition very close to the active edge of CLK1, thereby causing the second flop to go metastable. Now, there are several ways you can prevent this to happen, and these are called all reset isolation strategies, where either the data path between these two flops or the clock path to the destination flop are gated. Now, there is an inherent assumption when I'm doing a structural analysis, say RDC analysis on my design, there's an inherent assumption that when I have my isolation logic enabled, then the path between the source and the destination flop cannot be sensitized. This is the assumption I make when I waive off this violation, saying that I have an isolation strategy in place. But the question is this assumption valid? Do I verify this assumption when I do a functional verification? Again, this indicates there is a missing verification linkage when it comes to validation of waiver related assumptions. Now, talking about metastability aware verification, there can be multiple scenarios where metastability can cause a functional failure of the design. The first one is a classic example of a CDC convergence where two paths are converging into some combo logic through synchronizers. Now, if they have a timing relationship, if there exists a data coherency on the inputs, it's not guaranteed that the output of the synchronizers would have that same data coherency because of this unpredictable delay in the synchronization paths. So this is something which is an effect of metastability. Similarly, if I have a FSM with asynchronous inputs coming in, so after synchronization, these signals can lose their timing coherency, which can cause an undesired state transition happening, which in the worst case could be a deadlock or a live lock state, and that can cause the FSM to go for a toss. Similarly, for asynchronous FIFOs, we know that for calculating the full and the empty conditions, we have the pointers synchronized to the other side of the, from the read to the right or right to the read. Now, in these scenarios, if there are issues due to metastability, so there can be data integrity issues with such asynchronous FIFOs. Now, this is just a few examples. There can be multiple such scenarios. Even not just functionality, even performance can be affected when metastability occurs. Now, why we are not able to catch or comprehensively verify such scenarios with our current methodology today? So if we look at, typically this kind of thing is done in simulation with some synchronizer, special synchronizer models with built-in randomization. So what it does is it tries to randomly delay the output of the synchronizer by a cycle. Now, when we try to model this with one cycle delay, it actually models the setup violation only. But as we know that if there is a hold violation, the output can actually appear one cycle in advance as well. Those type of violations are not modeled by these structures, And also, only those paths where you have such special structures instantiated, those paths would be subject to such random delay. And as we know that most of the solutions today work on with simulation. So what we understand is that to do a comprehensive metastability aware verification, we need to have an accurate metastability modeling capability where we model all effects of metastability, and at the same time we should have some advanced features like injection capabilities to inject metastability related effects and see that whether my design is still immune to metastability. So with that, let's look at how a true CDC RDC sign-off flow should look like. Now, these are the two steps which are done in any conventional CDC RDC sign-off. The first step is to do a proper CDC configuration where the user would be specifying clock specifications, reset specifications, and CDC constraints. And then we know that what are the set of comprehensive structural checks that needs to be done. Once the structural checks are run and there are a set of violations reported, the user would review all those violations and create a set of waivers. Now, this is the conventional CDC sign-off flow. But as we have seen, there are several gaps in the conventional flow to kind of make it comprehensive. What we need to do is to add a functional analysis and metastability aware analysis in our sign-off flow. In the functional analysis, as we have seen, that we need to do the constraint validation, the waiver validation, and also the protocol checks for the synchronizers I'm using in my design. And when it comes to metastability analysis, we need to do a metastability aware verification for either in a formal or in a simulation based environment. We can use assertions, we can use a simulation test cases. And in addition, what we can do is all these checks that we have generated or used in functional analysis can also be enabled when we are doing metastability aware verification to ensure that none of these things break under metastability effects. So the first piece of this additional step, let's look at the functional validation of constraints. Now in JasperGold, you can automatically generate these assertions with the push of a button. It's a push button flow, and you can prove these in formal verification. So since JasperGold CDC app is built on top of the JasperGold formal platform, you can prove all these auto-generated assertions in formal. Now, some of these constraints, like a static constraint, has a pseudo nature as well. So let's take an example. In this example, you see there are two flops which are connected, and there is a CDC crossing between them. Now, there is no synchronizer here because the expectation or the assumption is that when the source signal D2 changes, then the destination is under reset, which means RST2 is asserted. Now, if I specify D2 as static, then any formal proof will tell that this is a failure because D2 can change. And we know D2 can change, but only under a specific condition. So it's important that the tool allows you to specify a condition along with the static declaration so that it can be formally or functionally verified. And this is what JasperGold allows you to specify a condition which says that only when the reset is asserted, that's when this signal will remain static. Now, this would trigger additional verification of the pseudostatic property. But at the same time, you can also export these checks and run them in simulation, which guarantees that the constraints that you are using for your CDC analysis also exist and the environment is same in simulation. This way, you can actually build confidence on the quality of your constraints, thereby having a sound structural analysis. Now, coming to validation of CDC protocols, we know that every synchronizer is supposed to follow certain protocols. Now, these protocol checks can be automatically generated for all identified synchronizers. Again, it's a push button flow. And JasperGold also supports specifying protocol checks for user-defined or custom synchronizers. You can specify those checks and the tool would automatically replicate it for all instances of such custom synchronizers. So typically we have seen people running these protocol checks in simulation because of lack of formal capabilities in their tool. But with Jasper Gold, because of its best-in-class formal engines, you are guaranteed for a much better proof convergence. And as just we have seen for constraint validation, even for CDC protocol checks, you can export these auto-generated checks and run them in simulation. Now, this is a list of protocol checks. It's not an exhaustive list, but it's kind of an indicative list of the kind of protocol checks Jasper Gold is capable of generating, and also the synchronization schemes that are supported for automatic identification. And as you can see that most of the synchronization schemes are covered, and they are also covered under the protocol checks. Coming to validation of waivers. So as we have seen that we do make assumptions towards design functionality while waiving off violations. Now, it is important to validate these assumptions while you are dispositioning the structural violations. When you do that, Jasper Gold is capable of generating or identifying such conditions under which you can actually automatically waive certain violations if those conditions are proven to be valid. For some examples could be that buses are gray coded, or there is a CDC crossing but its metastability safe because it cannot be sensitized. And there are scenarios where the tool is not able to identify conditions. In those scenarios, you can also provide an SVA expression as the waiver condition. What the tool would do is, so it would prove that condition informal, and if it is proven, it can waive off a set of violations which have been specified by the user, saying that you can safely waive these violations if this condition is true. So as you can see that we are actually capable of using formal verification to reduce the structural noise, and you can also at the same time, if you want, you can export these conditions and run them in simulation. So as a result, we can reduce verification noise by using formal verification, and at the same time, we are actually avoiding any manual errors that can creep in when you are manually dispositioning or waiving off such violations. Coming to metastability injection flow, so Jasper Gold supports metastability injection in both formal and simulation. The prerequisite for both the flows is that for formal, you have a set of passing formal assertions, and for simulation, you have a set of passing test cases or assertions. So in formal, the first thing you do is to provide some user written assertions. And as we have seen, you can also enable the protocol checks or the waiver checks. And the tool, again, it's a push button flow. The tool would inject metastability effects into the design and prove those properties. If it fails, you know it is because of metastability. So you can open visualize to see the counter example, and there is some special customization done to show you that how the tool would or the design would behave without metastability and how it is behaving with metastability. So you know what was the expected behavior and what is the current behavior to understand the injection results. Similarly, in simulation, you can pass on this information in form of timing violation monitors and injection modules to simulation. All you need to do is to include these metastability files into your simulation run file, and when you run simulation, your simulation becomes metastability aware now. And if any of your previously passing test case fails, you know it is because of metastability. Then the debug process is still the same. You open either Indago or SimVision, and there are injection witness signals, special signals provided by these monitors, which you can uh, plot on the waveform, and you can understand the injection behavior. Now, there are certain customizations in terms of helping you to understand the behavior of the injection. You can control this by selectively enabling or disabling any CDC crossing. So the tool would follow your instructions of whether to inject or not. And also, you can at the same time use modes like auto always injection or no injection in simulation, which would let you to identify violations or failures, metastability related failures quickly, or just to mimic the metastability behavior and see whether your injection is happening for every crossing or for a specific scenario. At the same time, as I mentioned that in both formal and simulation, you can enable the protocol checks and waiver conditions during metastability injection flow. Now, coming back to the true CDC RDC sign off with JasperGold, how would it look like? So in addition to the standard conventional steps, we would have a functional analysis where we can do this constraint validation or signal configuration validation. We can do waiver validation and a CDC protocol check verification. We also have some clock relationship checks and the reset order or priority checks. For metastability aware verification, you can do it in both formal and simulation. In formal, you enable the assertions you want to verify along with the metastability effect. And in simulation, you can use both the test case and assertions when you run the simulation-based flow. So that's how you can actually shift left the metastability related verification into your RTL space. You can augment this with your regular CDC RDC sign-off flow to have a much more comprehensive and holistic CDC sign-off. Now, looking at the complete picture, so JasperGold CDC offers you a set of comprehensive structural and functional checks. And along with that, it uses effectively the industry leading formal technology to provide you metastability aware verification. We have innovative debug, and also as you see that we have used formal for doing conditional or auto waivers. With that, we would move on to the demo and show you how it looks like in the tool. So I hope you can see my VNC and the Unix terminal. So
Yes.
I already have a setup running. So let me, before I get into the details, so let me show you the run file. So as you can see in this run file, this is very similar to what Convert showed for Superlint. First, we load a rule file which decides what checks to run. Then we have the compilation of the RTL files. We can load the liberties and then we elaborate the design. Here I'm using an Ethernet MAC as my DUT. Then I load the SDC where I have the clock declarations, the clock relationships, and the set case analysis defined. Then we have the reset declarations. And this is what I was talking about, where we have the static declarations, and I have specified a set of conditions which tells that these signals would be static only when these conditions are true. Then I have a few false path declarations followed by the actual commands that run the structural analysis. Now coming back to the tool, so I have already run this run file, and this you can see that the tool has reported a set of violations. It has a very similar or almost the same look and feel as Superlint. This is the violation tree where the bunch of violations have been reported. Now here, if you see, there are some no sync violations reported, some convergence violations reported, and there are some reset related violations reported. So there are two domains, CDC and RDC, under which all these violations are getting reported. Now, in this demo, I'm going to show you three things. First would be the constraint validation. Second, I would talk about the waiver validation or the auto waiver flow. And then we would see also a metastability aware verification, informal. Now, for the constraint validation, let's look at this table, which has a list of signal configurations here. So if I scroll down, as you can see, these are all constant declarations coming from the SDC. But if I go to the bottom, you will see these are the static declarations which comes from the run file we saw just now. As I mentioned that this is a push button flow. So there is a button which kind of proves the signal configurations. If I click on this button, the tool would start proving. And as you can see, there is one uh, constraint which has failed. And when it has failed, the tool reports an additional violation on the violation tree saying that this signal is not static. To debug what happened, I can do a debug violation here, and the debug is context specific. So since this is a functional failure, it would automatically bring up a waveform window. So as you can see here, this is the register. And if I go back to my run file, this is the last declaration where you can see the condition is regcs2 should be 0 for this register to be static. Now, here you see that regcs2 is all 0, but still my register is getting written into. So what I'm going to do is I'm going to right click on this and say why. This will bring up the source code browser and it'll show me why this register is being written to. As you can see here, this write signal is actually getting active, which means there is a write happening. I'll double click on this to still trace back on its driver. And as if we trace back, you see that there is a CS signal, it's a chip select signal, where one of the bits is 1. Now, if I trace back further, you will see this is the reg CS3 signal and not reg CS2, which is going high and which is causing a write to happen on this register. So I intentionally made a mistake here by mentioning this as reg CS2 to show you that if there is a problem with the specification or with the design, the tool can actually catch it and report it to you. Now, going back to the tool to show you a waiver validation, as you can see here, we have 2 no-sync violations and 47 convergence violations. What I'm going to do is I'm going to generate some waivers. So the command is check CDC waiver generate. So it will generate a set of waivers. If I go to the waivers table, you will see that there are some auto waivers generated with the status as not processed because we have just generated it. We have not processed it yet or proven it yet. So now I'm going to prove this. Once I start proving, you will see that some of these start changing its status. The status changes from not processed to safe. And similarly, if you see the number of violations in this violation tree keeps changing now, as you see that 2 of those no sync violations are now gone because both the metastability safe checks have been proven to be safe. And if you look at the convergence violations, it has reduced from 47 to 28, which means that this way we can use this auto waiver flow to run formal analysis in the background to avoid doing any false assumption towards waiving of structural violations, but at the same time reduce structural noise using formal. Now, what we are going to do is to move on to the metastability aware verification. For that, I'll quickly go back to my slides and show you what is the duty looks like. So I have a duty where I have 2 blocks, the control block and the FSM block. Both blocks have a counter each, and there's a common counter enable signal which drives these 2 counters. So the counter in the FSM block receives the counter enable signal directly because it is in the same clock domain, but the control block receives it through a synchronizer. So the expectation is that the counter in the control block will follow the counter in the FSM block after 2 cycles because the enable signal would reach the counter after 2 cycles once it is asserted. Now, switching back to my Unix environment, I already have a session running where I have this property and I have already run it and it is proven. Now, what I'm going to do is, again, as I mentioned, this is a push button flow. So what I'm going to do is I'm going to click on this button and it will inject the metastability effect into the design. And once you do it, it will tell me that there are how many CDC crossings where it has the potential of injecting metastability. In this case, we have just one. And if you notice, the status of these properties have changed now. Now, again, I'll click on a button which will prove these properties in presence of metastability. And as you can see, now this property fails. Now, if I go here, you see there are two violations which says that the metastability related failure has happened. Again, I'll debug this violation, which brings up the waveform window. And this is the counter enable signal. So if you see the counter enable signal, this goes high in the first clock cycle. And this is the register. This is the first flop of the synchronizer. Now, this is expected to see a rise in the second clock cycle because the counter enable is high in the first cycle. But since the tool has done injection here in this second cycle, it forces the flop to miss this pulse. As a result, the counter in the control block does not count, whereas the counter in the FSM block keeps on counting. So when we compare these, so we see that the assertion fails because the counter block control block counter never counts. And as I mentioned that we also show you the no MSI or the no metastability injection behavior of the flop, which shows that this was the expected behavior and this is the actual behavior. And this is how you can identify what are the issues in um, your metastability related problems in the design. So with that, I'll switch back to my slides and kind of conclude our discussion today. Okay, so conclude on this LINT sign-off takeaway. As you can see that typical structural LINT is not comprehensive and you need to augment it with auto-formal checks as Kanwar has said. And to do that, you have the industry-leading solution in form of JasperGold Superlint, which gives you a comprehensive set of structural LINT and DFT checks, high-value auto-formal checks as we have seen, and it's easy to set up. It's a feature rich when it comes to analysis and debug environment. And also it is designed to be a low noise and high productivity solution. On the CDC RDC sign-off takeaways, again, as we have seen that structural CDC RDC analysis is not enough. It's not enough for a comprehensive sign-off. So we need a linkage with functional verification to achieve true CDC RDC sign-off. And towards that, JasperGold CDC app helps you to achieve this with a comprehensive set of structural checks. It adds the functional CDC RDC verification capabilities in form of constraint validation, waiver validation, protocol verification, and metastability aware verification. So that's all from our side today. Thank you for listening to us. Now it's time for questions.
So I think you can add questions on the chat. We'll take it there, or even feel free to unmute and ask your question. So I see one question in the chat. So how does JasperLint cope with designware? So designware, being a library of components which I think goes with the synthesis tools. So you can configure JasperGold lint to say that this is a pre-verified library, and I do not want to do any checks on inside the designware, but consider it as part of the design and do the rest of the checks. So you can configure JasperGold to understand the designware. Hope I answered your question. So please type in your question in chat. And if you want, you can unmute and ask your question.
Okay, so let me take this. So the question is that the metastability injection is run first in formal and then optionally passed to simulation. How does this work if I am running CDC analysis on a multi-million gate design? Formal works best at block levels. Um, so I won't say that this is like a flow that you have to run formal first and then simulation. It's a parallel process. So if you do not have a formal environment, but you have a simulation, so you can directly go from CDC analysis to formal, so to simulation to run your metastability aware verification. So typically, as you're right, that formal has its limitations when it comes to the size, depending, of course, on what kind of design you are running and what kind of properties you are running. But yes, if there are difficulties in running formal on a multimillion gate, you can always directly move from your CDC analysis to simulation. For that, all you need to do is to generate those timing violation monitors and the injection modules from JasperGold and pass it onto your simulation environment. I hope that answers your question. Any more questions? Probably we have maybe another couple of minutes left. Feel free to unmute yourself in case you don't want to type.
Last call for the questions. I think we have less than a minute left before we wrap up the session.
So feel free to contact us in case you don't have any questions right now, or maybe you want to, it pops up later on. Feel free to connect to us and send out your questions to us on our email. So we'll be happy to answer any queries you have.
All right. Thanks everyone for your time and have a good rest of your day. And thanks again for listening to us. Thank
Yeah,
you
thank
and
you
bye bye.
everyone. Bye bye.